Look inside. First step is to remove or lift up these 4 tabs. I'm going to use this sharp straight edge screwdriver just to wedge underneath those tabs and lift them up. They're pretty tight when you first get started. You may need to use something even sharper, like maybe the sharp edges of some cutters. Just be careful not to cut them off. Alright, with those lifted up, the entire body of the pot just pulls away. Now the shaft connects through the phenolic wafer to a plastic disc on the back. The plastic disc has been crimped onto the shaft, and there's no easy way to get that off without damaging it, make it impossible to put it back together. So I'm leaving it on there. You can see that the plastic disc underneath it has this wiper, which has a dimple in it, and the dimple is touching down onto the phenolic wafer in one place. Now, printed onto the phenolic wafer is a ring of conductive carbon material. You can't really see it under this, but it's printed connecting from, it comes out from this lug, see that little black strip right there. It comes out and it's printed in a big circle around like this, and then connects up on this end like this. That amount of conductive material is what determines the resistance of this pot. In fact, if you just take your multimeter and connect it across these 2 lugs, it doesn't matter where the shaft is, that tells you what the overall resistance of the pot is. And it's based on the amount of carbon material printed there. Let's take a quick look at another brand of pot because it's easier to see inside than the Bournes. This is a CTS brand pot, and it's put together pretty differently from the Bournes we were just looking at. Now I've already lifted up the 4 tabs so that we can easily pull this off, and you can see that this threaded shaft is pulls off completely separately from the rest of the body of the pot, allowing this wafer just to come off totally separately. And that's pretty different from the Bournes, in which the wafer was integral to the shaft and the plastic disc. You couldn't pull them apart without damaging the pot. Now in this one you can see both the outer and the inner wiper and the outer and inner rings here. And we just couldn't see on the Bournes. This inner ring here is raised up a little bit and it's connected directly to the center lug, and you can see the inner wiper here rides on that ring while the outer wiper rides along the conductive ring. And this wiper is actually got 2 raised lips which push up against the conductive material on the ring. They push with a fair amount of force, and that combined with this grease that it's riding on here make this pot a fair bit more difficult to turn, although it feels pretty good. Unlike the Bournes, which is really easy and light to turn, this one, once it's all sort of pushed down and compressed together, takes a fair amount of force to turn, but it feels nice and stable. And I think you can see from the construction and the way I just put that back together, this is a really well-built pot. So now the way the pot works, when you turn the shaft, as I mentioned, that little dimple in the wiper is touching that ring of material in only one place. What you're doing is making a connection between this lug right here through that carbon material that's printed on the wafer to the dimple in the wiper, which then connects to the center ring and out through the lug. So the amount of resistance is determined by where the dimple is touching the outer ring. For example, if I point the dimple right here, so the dimple is very close to this lug, the distance between this lug and this lug is extremely short, almost no resistance. What it's doing is coming in here, touching the dimple, going to the center ring.
Alright, so there's the inside of those, and just that review, when you compare those ones to these big wire wound heavy duty dudes, they're doing the same thing. It's just the capacity of the little one is not nearly what the capacity of the big one is. As Dean would say, if you overdo it, they'll go poof, and the smoke comes out. And most of our electrical components work on smoke, so once the smoke comes out, they won't work anymore. Alright, looks like Pascal is the only one missing. So we got that taken care of. Alright, charge your batteries? I had a bunch of people ask me yesterday, and I'm gonna have to go back in and probably change that to say amp rating that you charge your battery. Because unless they were coming up with some term that me and Dean don't know, basically they were saying at the constant current portion of your charger, hey, how many amps were you using to charge it? So those chargers often have a 2, a 6, an 8 amp rating. So it's just asking, hey, which rating did you use for charging up the battery? So that's clarification on that. Any kind of questions on your batteries as you're doing it? Was that going along okay? All right, cool. Today we are talking mostly about wires, exciting stuff. We're gonna take it at a pretty low level. We're definitely gonna dive back in deeper in airframe and a little bit back in power plant. So you'll get a review of this, but laying the foundation, I guess you'd say. These 4 things we're gonna hit, each slide will come through and cover each of them. But now that we know how to do the math on our circuits and all that, and we've been assuming our wires are 0 resistance, we're actually gonna come back in and say, well, there's a little bit of resistance. You're not really gonna put it into your math, but it's the reality of we have electricity flowing through a wire, and there is resistance there. So there's 4 factors that affect conductor's resistance. There could be more, but these are the main big ones. One is material, so what material it's made out of. Is it copper, is it aluminum? Those are our big 2 in aviation. You're not gonna see much else. You're gonna look at a fair amount of wires, and you might say, hey, what is that thing? Is that stainless steel, especially like bonding wires like this one? And I'll pass this around just for the fun of it. So take a look at it. Most of the ones that look like they're a stainless steel or something are not. Almost all of our copper wires are coated with something to keep the copper from corroding. So it'll be like a tin coated or something they put around the outside of them. So typically our wires are gonna be copper unless we're running long lines or the manufacturer had a reason to use aluminum, but pretty much copper. And if you were to take like a really fine grinder to that thing, you could actually kind of grind off the coating and see the copper come through on most of those, and you go, oh, okay. So the material it's made out of is huge, and we love copper. The length, obviously, that's just math, right? The longer the wire, the more the resistance is. The thickness of the wire, we call that gauge. I'm throwing up here a wire gauge meter. You need to know how to work the thing because it shows up in like prep work questions and on your exam. But if you're actually working on an airplane, that wire better be labeled, and we're gonna cover that today for how thick it actually is, but thickness or gauge, and then temperature of the wire. Just like our light bulbs, the hotter the wire gets, the more the resistance goes up. So depending on what temperature the wire is, that affects it as well. 2 factors to consider, these are the big 2, is we're gonna have a slight voltage drop on the wire when it goes from wherever you took the power from, maybe your circuit breaker and your control panel, out to the device. Because there's resistance, there's gonna be a voltage drop, right? Amperage across the resistance will give you a voltage drop. And the other one is because there's a voltage drop, that means we're gonna be making some heat. And we gotta get rid of that heat, because if we don't, if it's just building, our wire gets hotter and hotter and hotter. So this slide pretty much covers everything we're going over today. When we talk about thickness, we need to start with our wire gauge. I'm gonna grab a marker. So pretend with me, this is 1 strand of copper. So like 1 strand out of here. Maybe this bottom picture would be good. Now it's not the insulation, it's just the metal, it's just the copper. So if we wanted to use this wire gauge, we would bring it up here and we would see, hey, which one does it fit right nicely in the flat section? So I'm too big for that one, too big for that one. Oh, it's right about there. Actually, it might be this. So, if this was sized properly, my marker would be a 9 gauge. And as you see, it goes like a shotgun in that the smaller the gauge is, 1, 2, the larger the wire is. The higher the number gets, the smaller the wire is. So it's backwards of what your brain might tell you. So we're up to 9 gauge on here, and I really want to point out my marker actually fits inside. Oh man, I can go way down here. Picture seems like it's getting funny. My marker fits inside this 21, but emphasizing it's not the hole, it's the slot that it fits in. Everybody getting that, understand that? That is an exam question, and you need to absolutely make sure. So that would be, theoretically, if I'm using that, that's a 9 gauge if I was going to slide my wire in and measure it. So, the issue with that is most of our wires that we use are what we call stranded wires. So here's a blown up view of one where it's not just one solid piece of copper like you get down here, it's multiple pieces inside. That helps them be flexible is basically the main thing. In our aircraft, there's vibrations, there's moving stuff like that going around, and the solid wires, well, they're just not as flexible. They'll end up being more brittle because they're moving around. So they'll be made up of typically many conductors inside one wire. So we call that stranded as opposed to solid. Now, I don't get to just grab my whole bulk of stranded and come up here and say, nope, doesn't fit. Doesn't fit. Oh, I'm getting closer. 6. Obviously the sizes are wrong because it's a projector. I don't get to just do that. It's not quite that simple, Corbin. Depends who you ask, and we're going to get to that. So, the reason I can't just take that big bundle and do that is I had to go digging, but I found this. And basically what they're showing is the standard stranded, looks like this one. They make a compressed stranding, which basically you're kind of standard on the inside, but they essentially squeezed the wire down when they made it, and it makes it a little smaller. Notice it's not as thick, it's a smaller diameter. It's the same amount of wire in there, they're just compressed down a little bit tighter. And they even do one that's really compressed. Now, these are not something you're really going to see in aviation, but I'm just driving the point home. This has a lot of air gaps in between all the strands, right? And what we actually want to know essentially is we're looking at that and we're looking for the surface area of that wire, and that's what determines how big of wire we have. So what we actually would do, is we would pull one of our strands out and we would go over to our gauge and we're going to figure out, and obviously this isn't working really well because of the pixels, but we're going to figure out what size that one strand is. And let's say I find it's 29. And then we're going to go to a chart, which we'll show you in a little bit, and we're going to figure out basically the area. They call it circular mills. We're going to figure out basically the area of that and multiply it by how many strands we have, and that's how we come up with our ultimate gauge size. So when we're using that, we measure the individual strand, and then we'll use the chart, and I'll show you how to do that later. They're kind of showing you the picture here. Now, I don't even know if we have one of those around here, because our wires always should be labeled is one thing. The second thing is, it's not the most accurate in the world. But most of our wires are going to be closer to this size. This, I think, was a piece off this roll, which, let me read it. 12, it says. This is 12 AWG, 12 gauge. it's made up of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 strands. Those are pretty fine. I could take one, because this tool's about this big, and try to find it, but more accurate, you can grab a micrometer and measure it, and when we get to the chart, you'll see. But easier around here to grab a micrometer if you get somebody asking you what it is. And who has that little strip I passed around that looks like it's not? Yeah. So I think it's airframe. It might be power plant because we'll use those for bonding. Those aren't even round, right? It's kind of a ribbon. But you can do the same thing with those. There's a bazillion strands in there, but you can grab a micrometer, you can measure one, you can take about 30 minutes and try to count through how many are in there and do the math, and you'll end up with your total gauge. So just because it's not round, we don't really care. Corbin?
What are the holes?
Gives you flexibility, I don't know. Yeah, they're not in for anything. It's weird. Gives you a slot, I guess. Maybe it's so when you push it through, you got a way to take it out. I don't know. So, that is the basis to our stranded versus solid wire. Oh, I do have on here circular mill. A circular mill is, they'll call it a unit of area equal to the area of a circle with a diameter of 1 mil. So 1 mil being like is it a millimeter diameter? There's a number there. But point being, it's a measurement. They converted it over to, it might be 1/1000 of an inch converted over, but when you see that word circular mill, it is a specific area. Very, very small, but it's a specific area. And I don't have it today. I think maybe we do it in airframe. But the idea is it's 1/1000 of an inch times pi times whatever. But it's a term that's a specific area. So switch the slide over here. We got a blown up of stranded and solid. And just reviewing stranded, it moves really good. If I got this in an airplane and it's moving around, I'm going to say a little bit. I mean, probably this, it would fail eventually. But if it's moving around a little bit with vibration and whatnot, this thing's not going to mind. And it's quite flexible, so wherever the terminal is on there, it's not going to be pulling off. If you've ever worked with solid wire, it's not that way. One of you guys had a solid jumper wire. We were working on something. Oh, was that terrible? Because it doesn't want to stay where you put it. So we love stranded. In airframe, we're going to talk a little bit more about the difference between cables and wire, but this slide down here, I put in to kind of introduce the word cable. So in aviation, cable is going to be when I have more than one wire inside of another insulated sheath. So if I said it's a stranded wire, basically the electricity can jump in between all of those individual strands and they're all one happy family. But if I insulate those and then I put a couple of them next to each other inside of another sheath, we're going to call this a cable. So this is a stranded wire. This is a stranded wire. This is a cable with 1, 2, it's hard to see, but 3 stranded wires. This is a cable with 1, 2, 3, 4 stranded wires, and you get the idea. So when you hear cable, think multiple wires. Now when we use the word conductor, technically each strand in there is a conductor, right? So a conductor, you could say each strand is a conductor. All the conductors together make up the wire, but a conductor is anything electricity can go through. So if you see the word conductor, kind of stop and slow down a little bit and say, were they asking me like one strand? Were they asking me the whole wire? Were they just saying the frame of the airplane's a conductor. So that's some terms that we go over. Conductor material. So this is in, I think, AC 43, and this one says current carrying capacity and resistance of aluminum wire versus current carrying capacity and resistance of copper wire. So we're just going to compare aluminum to copper here. Copper is a better conductor. It's a little bit stronger. It deals with the stress and vibration better. And it will have coatings to keep it from corroding on there. Typically tin is what we coat our copper with, but depends on the manufacturer and what they're doing. They can be different things. If you notice on the aluminum, is it aluminum one? Yeah, they don't give you a below 8 gauge. And when I say below, they don't give you a number higher than 8, which means the wire is getting smaller and smaller. There are aluminum wires that are smaller and smaller. You can get aluminum wire that's 14 gauge. Typically, the reason we use aluminum wire is when we have to run longer runs, long distances, and once we're down to these real small wires, most of the manufacturers are going to go, you know what, it's not worth the extra risks with aluminum, we'll just do copper because it's not that heavy of a wire anyway. So let's just pick a number out, and we'll pick the 6 gauge, and we'll talk about temperature later, but the temperature does make a difference. Just stop in a second because I'm looking at the chart. 105, 150. Good. My dyslexia kicked in. I'm like, it's the same number. So we'll pick 105 degrees Celsius with our aluminum wire. And we'll go 6 gauge, 105 degrees Celsius. And it's in the very most basic general terms, it's essentially saying that aluminum wire can carry 40 amps in it. So that's the most basic general terms, and we're going to cover why I say that in a minute. If you come all the way down here, it'll say it should be 0.427 ohms per 1,000 feet. So that's pretty general for aluminum. If we go to the copper one, 6 gauge, so the same number of circular mills, the same area, if you will, we get 50 amps. So I can actually carry a little bit more load, and 0.44 is what I'm reading there for ohms. So similar ohms. It actually says it's slightly more ohms if I'm looking at that right. Oh, that's what I did wrong. That's not what I had written. Anybody catch what I did wrong? My page has a bend in it. Second one, third one. My math wasn't mathing. Hard to tell on a curved page on a flat screen. So the aluminum one is actually 0.641. It's a higher resistance per 1,000 foot of ohms than what our copper is. There we go. Thought I messed up the whole thing. So that's part of how copper is a better conductor. So you'd say, well, why would I ever do aluminum then? Well, the answer is if I had, I don't even know what gauge this is, 0, something like that. If I had the same length of copper wire, it's going to be much, much heavier than my aluminum wire. So if I had to run something like this all the way to the back of my 747 airplane, or where you'll sometimes see it on small aviation is if the battery's in the tail of an airplane, they'll do that for weight and balance sometimes, and you got to do a 30-foot run to get the battery power all the way up to the engine and the starter. Every once in a while you'll see where they were like, hey, we can save like 2 pounds if we run aluminum wire. And they'll run an aluminum wire from the back up to the front. But in order to carry the same capacity, what they'll end up doing is they'll run in this case, they might run a 4 gauge where they can get essentially the same amperage out of their aluminum wire. And it'll still be lighter, but with the various strength, corrosion, and other issues with aluminum, you just don't see it much anymore. But you do need to be aware that whatever material your conductor is, whatever material your wire is, you got to be on the right chart and have the right one. The length of the conductor obviously is going to contribute to the resistance. This one's in your actual book. It's hard to read the numbers from where you're at, but this says gauge number, and then it'll say diameter, and it's in mils, and that's where it goes back to, it's like a mil's a thousandth, right? So it's thousandth, I believe, of an inch is what they're measuring there. And then circular mils is they just convert my diameter into circular mils. So if we really wanted to be math people, if we found our 100 transfers over to, it's actually 10,000, so the math's not perfect. So anyway, it also gives us square inches. If you're like, I don't like circular mils, I don't like that number. Well, square inches is just, you take your circular mils and multiply it by some sort of exact equivalent. And then you get ohms per 1,000 foot. And because the temperature makes a difference, that gives you a couple different temperatures. Here's one at 77 degrees. I think the next one's at 100 and something degrees. So there's an old electrician trick, hack, is they carry these rolls of wire around in their truck, and they might have used 100 foot off the roll, and they got to go pull a wire, and the blueprint says, I need 400 foot of wire. And they go, I don't know if I have 400 foot on there, but I don't really want to spread all across the floor just to find out it's not and put it back on. So they'll go to a chart like this. This one's 12 gauge, I think we said. So they'll go to the 12 gauge, run it over, say, okay, it's 77 degrees outside. It should be 1.62 ohms per 1,000 feet. They'll grab their trusty ohm meter. I say trusty because, well, if your ohm meter is terrible, you'll regret it. Check the ohms. Now, I know this is going to be really low resistance because, well, it is. So I'm not so worried about it going through my fingers. My fingers at the moment are 300,000 ohms, so 0.3. So I'm just going to clamp it in to make sure I get a really good connection. And I'm getting 0.6 ohms. If I wanted to double check myself, I could do it, without clamping my fingers in. 0.6 ohms, so I'm basically getting the same thing either way. I'm just curious. Grab a cheap meter. What do you think? Is it going to be the same? .7 ohms. Now, which one do you trust? Have one of you guys check it later with your meters. 2.3 ohms. All right, so you get the idea. You can only use that trick if you actually have a meter you trust. But we could grab our calculator and say, okay, if I have 0.6 ohms and it's 1.6 per 1,000 feet, you run the math, and that would give me somewhere around 300 foot, I think. Calculator, anybody? Whose brain's feeling mathy today? No mathy brains? Everybody's like, no, I'm out. It's Tuesday. 1.6. All right. 375 feet is what they're saying I have on there. Now, I don't know if that's right. Is anybody electrician? What normally comes on one of these? I think that's a 500 foot roll. So 375 sounds like it's in the neighborhood. So you can actually do that, and the reason I did it is just to get the point across. You guys aren't going to be running 375 feet to have to do that, right, in aviation. But each foot has a certain set resistance, and you can run the math if you want to see, hey, how much resistance is in this particular wire that I'm running electricity through. Make sense so far? Good. All right, if the temperature goes up, the resistance goes up. So on my chart, if you go to the little bit more complicated one in the book, it'll say, okay, how many amps can run through a wire in your airplane? And it'll say, well, what's your wire conductor temperature rating? They're basically saying, what are we going to let that wire get to before we have a failure or we have a problem? And they say, if it's only rated at 105 degrees Celsius, which yeah, it's still like 220 degrees, right? I don't know if I want 220 degrees wires in my airplane, but if we take that number, we'll go with number 14 gauge, because that's a little more common. They're saying, hey, your 14 gauge wire, it's good for in the neighborhood of 10 amps. But if you have a wire that's rated to be hotter, we'll allow it to get hotter, we'll let you push 14 amps through. And if you're okay with your wire being 200 degrees, it's a 400 degree wire, Fahrenheit, that's a hot wire, we'll let you push 18 amps through it. Now you're thinking, hey Case, you said the resistance went up when it gets hot, right? I'm like, yep. So you would have a higher voltage drop as the wire gets hot. But basically, the way to kind of be thinking about that is the insulation on the wire is rated to be able to withstand that kind of temperature before it melts, it breaks down, it starts letting voltage through. And if I let my wire get to be 200 degrees, it's going to reject the heat a lot faster than a wire that's only 100 degrees, right? So if we're okay with the wire getting hot, we're saying, okay, it'll be able to reject the extra heat that's built up from our extra amperage. So that's essentially what they're saying in this simplified chart that they give us here. So it's kind of interesting how that works. Does that make sense? Any questions on why they would do that? Yeah.
What do you mean by rejecting?
So if you've got a wire, today's thing we're getting into, there is resistance. So if I push amps through it, I'm gonna have a voltage drop, right? It's gonna be tiny, but voltage drop. So if I have a voltage drop across this, now I can multiply my voltage by my amps and I'll have a wattage, which is work that's done. And pretty much the only work we're doing is we're making heat. So anytime you run electricity through a wire, you're making heat. So the more electricity you run through, the higher amperage, the more heat you're gonna make. And when you're making heat, it's gotta go somewhere. It's gonna build up. And if I have, let's say this wire is 70 degrees, is it going to reject any heat into the room? Not really, because the room's 70 degrees, right? There's no temperature difference. But if this thing's 200 degrees, hot, it's not only rejecting the heat into my fingers, but it's going to be radiating heat off into the room. So it's going to get rid of that heat, and it's just going to radiate it into the room. And the hotter the wire is, so the bigger the temperature difference is between the wire and the air around it, the, let's say, faster it'll be able to reject that heat, because there's a greater difference in the temperature of the room or the airplane and the wire that's running through. Does that make sense? Okay. It's all about getting rid of the heat from the wire. So that's actually why we have the next slide. If I run my wires all tied together really tight in a bundle like that, is that going to make it easier or harder for the wire to get rid of its heat? Harder, yeah. It's going to be like, hey, this isn't so easy anymore. Or even one more complication. Let's say we're running our wire in a hot environment, like right next to the engine, or somewhere that we need to protect it so we don't have heat from, say, the exhaust warming up the wire and melting the wire. So we go, hey, I think I'm going to put a heat shield on my wire so that I don't cook the insulation. Oh man, what did we just do as far as now can that wire get rid of its heat? We trapped the heat in that wire. So we don't cover that a whole lot, and the reason is typically when we're doing shielded wires like that and what you're going to see in here, it's just a short run and there's not a lot of heat being generated in it, and we'll have a little bit oversized wires. So we're typically not going to get as concerned with it around the engine compartment, so we don't discuss it. But it would be a thing. The big thing we discuss is we run wires in bundles all the time, and that very much changes how much heat gets rejected or how well it can do it.
So if you have something in a bundle like that, or if you have insulation that's too good around your wire, is it possible to start getting thermal runaway from that, like with the 910 batteries where it's...
Yeah, I don't know if I'd call it thermal runaway, but yeah, it'll heat up and theoretically could wreck them. Now, we're gonna be good aviation engineers and mechanics, and we're just not gonna size it. So we're not gonna make it so that would happen. But if you sized it incorrectly, yes, you for sure could have that. You're gonna start melting your insulation, and then once your insulation's bad, the voltage starts jumping through, and then you have a fire, and I got a video in the end on that. Try to keep you guys awake. All right, we're gonna take a break because we're gonna get into some charts, and I'm not gonna put you to sleep. So let's take a 10-minute break, come back at 5:02, get a coffee if you need it, do some push-ups, be ready to read charts. You guys are looking as sleepy as I am. Trying to like be all excited about this, and you're like, yeah, I can do some push-ups.
Tigers win?
Tigers won, 3-0.
Were you there?
Home run in the night. 100 foot over from where I was, standing in a walkway, guy on third, guy on first. Big swing out to the outfield. I had to run up and I'm looking over the fence and into the stand. Home run! And it's Cleveland, so everybody's like, they were pretty rowdy. But I was standing by 5 Tigers guys, so we're all high-fiving. Yeah! Yeah, it was good. It was good.
That's 4 Tigers.
It was,
Are there Mexican games held?
I believe they are, yeah. Yep. And then Saturday back in where Cleveland, if there is. So Scooble was the pitcher. I guess he's probably gonna be the Cy Young winner, big old pitching award like that. Yeah. So he was pitching. So even the Cleveland was like, we got to beat him the next 2 games so we don't have to face him again. It was pretty cool.
Yeah.
So, I was asking my cousin, I think he actually came up through the Tigers as like 2018 draft pick. So,
They gotta win.
Hopefully he's a loyal Tiger.
yeah, youngish.
So they each
It
won
was
one,
fun.
right?
It was fun. Okay, the question is how many I gonna do today? And not just gonna do a competition.
Nah.
So, I think I'm gonna try to get to my 30. That's what I'm gonna try it.
Gonna do your elevated legs?
Yeah. See if
I
I
gotta
can-
do elevated legs.
see if I can last.
Where's the big sponsor now? AVG-140. David's Cheers trying to run.
Talk about thermal runaway.
I did it. I made it. He's like, I'm doing 50.
No, I'm doing great.
Big defensive game.
Once I'm back into it, about 40 3 times a day like that's, I think that's sweet spot.
That's perfect. Okay.
You awake now?
A little wake. Little wake-ish. If you don't have AC-43 in front of you, probably be a good idea to grab it. I think I was supposed to say that before. You guys don't have to do this until like airframe or power plant, but we'll try one once here just to make sure I remember before I get back to airframe and power plant. We know it's a 12 gauge because it's printed on it. That looks like somewhere between 18 and 19 thousandths. Is that thousandths or is that hundredths? They don't go to
Is that the replay from last night where we were watching the highlights?
First one is 10, 7.
That's a tenth of an inch. 25, which is a hundredth of an inch. So that would be 25. That'd be hundredths. Hundredths of a big. So then I gotta go back to its. 180 thousandths. Let's see.
Huh?
Oh, times.
Do you want to get
It actually might be your airframe book.
Ah,
Oh, I didn't.
that would make
I
sense.
guess we have to add our other. Yeah, that's what I didn't do.
All right, welcome back. I'm just trying to do this and have the math work out right. Like I said, we're not necessarily going, it's not a lab to do this in this section that we're in. But I'm just introducing it to you so when you get a little further down the road, I'm measuring about 18 on this, which is I think 0.018 here. So if I'm getting a 0.018 and then I multiply it, I had 19 strands, I believe. I'm going to recount 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 strands. So I can go down to my basically 18 here, which would tell me each individual strand they're saying is 25, but I don't know if I'm getting the right number. I don't know if I trust it. I can go over to my circular mills, and that says each one of those strands has 300 and I think it's 320, but that could be where my math is off. 320 circular mills. Multiply my 320 circular mills by 19. 320 times 19. Did I do that right? Let me double check that. 320 times 19. 6,080. Oh, good. That was where my math was off. I fat fingered it. 6,080 total circular mills in that wire. So then I scroll down through this thing and I say, hey, where am I at with about 6,080? I'm seeing a 6,500 here. So that's pretty close. Ta-da! 12 gauge. So you'll end up doing that in either airframe or power plant. But that's the math. That's how you would theoretically measure a wire and say, what gauge number is this? And we're going to talk a little bit later today about why, but we'll get there. Wire bundle. Okay, back to our chart. So, what wire size are you going to use? Now, there's the easy way, there's the semi-easy way, and there's the really complicated way that I don't think I've ever actually made the math work out. So I'm going to say go with the easy way or the semi-easy way. And if you want to be an aircraft engineer for a job, you can go with the really complicated way that I can't ever get the math to work out. Maybe Martin, I don't know, but not me. So the easy way is you just look what the manufacturer said. You say, what size wire was that? You put the same size back in, right? Seems like the best way to go. But they like us to know the not so easy way. Let's say you're adding a STC to an aircraft. STC meaning you're doing an add-on part that the manufacturer didn't have, and you know how big a wire to run. Then we're going to go to our chart, and we're just going to check it on our chart. But we're also going to have to do a confirmation that whatever wire we picked is going to be good with whatever breaker or fuse we need for the, I'm going to say the word component, but we're going to backtrack on that a little bit later today. So the semi-easy way is what we're going to be talking about for the next 20 minutes or so. The semi-easy way is using the charts. You'll find this one in AC43, and they copy it and put it all over the place. It ends up on writtens, on exams, and all stuff like that. If you have a 14-volt system, the allowable voltage drop across the wire you just ran is a half a volt. So basically, if you start off with 14 volts at your circuit breaker, they're saying, you know what, as long as your component is getting 13.5 volts, we're okay with that. If you drop more than that, we're not okay with that. Now that's for continuous operation. They also say, you know what, if you're not using this all the time, we'll let you drop more voltage. You can drop a whole volt on your wire. So you might only have 13 volts down at your component that you're working on. And the idea would be, if you're using it all the time, we don't want as much voltage drop because we're going to be kicking off too much heat, right? But if you're only using it part of the time, yeah, your wire might start to get hot, but you're going to shut that thing off pretty soon and it'll cool back down. So that's the difference between intermittent and continuous. There's a pretty big discussion that you may or may not get to the bottom of if you want to discuss it in round and round and round. And the discussion is your landing lights on your aircraft, especially when they're incandescent. So old style, most aircraft are going to LEDs now because they take less power. But there was a question on, are your landing lights continuous or are your landing lights intermittent? They used to be considered intermittent because, well, you just kick it on to land, right? Well, nowadays the FAA likes to tell the pilots to leave your landing lights on when you're flying so people can see you for safety reasons. If they wired the aircraft thinking they were intermittent and you're leaving them on all the time, well, we got some issues. So it depends on who you are and if you're running the wire. But really what it gets back to is, are you guys manufacturing the aircraft and deciding what wire goes to the landing light? No, the manufacturer will do that for you. So that particular one, really it's a non-issue for you. But that's the difference between intermittent and continuous is, hey, how often is it getting used? I think I have a slide that comes up, but I read somewhere what they would say is if it's less than 5% of the time, so out of every, say, hour of flight, is it being used less than 5% of that? That's kind of where they go. So stuff like landing gear is typically intermittent because I might put it down, it runs for 30 seconds, and then it's not running anymore. So my hydraulic pump for my landing gear is going to be an intermittent. Flaps would be probably considered intermittent because I put them down and they stay there. Unless you're a firefighter, but you get the idea. All right. You get the different voltages I want to point out. So 14 volts, 28 volts, 115 volts, 200 volts. This little chart is going to show up on later charts, and on your writtens, they might ask a question looking to see that you know how to read this chart. And that's cool if you can read this one. And there's also going to be a bunch of other charts that you can do the whole, hey, I saw that on a different figure on my written. Why don't I just go grab it off that one? And usually what it'll be is they'll ask this one. They'll be like, is a half a volt okay, or is it a 1 volt drop on a 14 volt? But we'll get there a little bit later. Where it shows up, these didn't come through the best. But when we get to our wiring charts, which we're going to get to today, figure 11.3, I believe that is, in your book. I'm going to make sure I got the right one, so I'm sending you to the right place. 11-3, and it's the figure, which is probably going to be page, I'm getting there. Page 11-31, paragraph 11-69, so whichever way you like it, you can take it. But towards the left side, you'll see that chart, and it gives you the same thing. So it's going to have voltage 200, 115, 28, 14. You'll notice sometimes those numbers are just slightly off. No, they're correct here. You might be like, but Case, I've got a 12 volt battery. Well, yeah, you got a 12 volt battery, but you also have a constant voltage charging system, right? And your constant voltage charging system, your alternator with a voltage regulator, it's going to be putting out 14 volts on your 12 volt battery, or 28 volts on your 24 volt battery. So that's why they kind of bump the numbers for you, because they realize once your aircraft is running, these are the common voltages that you're actually going to be running at in your system. So on that chart, it shows up for what the allowable voltage drop is. Now, there's two different charts there, whether it's figure 11.2 or figure 11.3. One of them is for constant. So this one says intermittent flow. And I'll notice if I go to 14 volt, intermittent flow gives me a 1 volt drop allowable. When I go to my continuous flow, it gives me the half volt drop. So it's the same chart if you look at the bottom 4 numbers and compare them to the top 4 numbers as what's back here. So it's just a good place to have a backup if you get that question and it's spread out. So, before we get too far and start sorting through these, I go back to, well, where's the absolute first place you look to say, what size wire should I put in here? Well, the easiest is it's probably printed right on the wire. If you have a wire in your aircraft that's damaged and you're replacing, it should be labeled right on the wire. And we'll definitely get that in more airframe, but just read the wire and say, what gauge is it? I'm going to replace it with what was in there. The second place, if it's not on the wire, maybe it's an old aircraft, you got an old wiring diagram like this, is remember your drawing classes, you got all these charts that you barely know how to read. On your wiring diagram chart, the wiring ones, it's hard for you to see, but this says GA, which is gauge. So if I had to go to whatever wire, well, that one's not labeled with a number. Whatever wire I got, let's say this one, PA15. PA15, I can find it on my chart, and it's 14 gauge. So I can go right to my wiring diagram, and it'll tell me what gauge wire that has to be. If I go pick another one for the fun of it, PA13, I can find, there's 15, 16, PA13. Hard to read on the computer, but I believe that's 18 gauge. So if you look for the GA on the key and just scroll up to whatever wire you are, that'll tell you the gauge. That's the easy way. That's what you should actually do as a mechanic. If you get into the chart we're going to go over shortly, I'd say you did something wrong or you're at A&P school. It's one or the other. That's generally where we're going to go with those two. So here's another chart. Is this one readable from where you are? Basically, okay, so I come up to my chart, somebody ruined one of my wires. I'm going to say it's wire PB17. So, we'll see if this works so I don't have to have all the fun. A mouse chewed through PB17, Gavin. What size wire am I replacing it with? Yeah, so he had a first spine PB17 here. Gauge is here. So 18 right there. Good job, Gavin. So that's the best way, that's the easiest way. You don't have to mess with the charts and yeah. But we got to teach you how to use the charts, why to use the charts. So assuming it's a new wire, now we have the semi-easy way or the crazy complicated way. We're going to go with the semi-easy way, is you just pull up this chart. Now there's two charts you see in your book, right? You got continuous or intermittent, so that's the first thing you got to decide. Are we continuous or are we intermittent? So this chart I pulled up is intermittent, so we'll assume that our device at the moment is an intermittent flow. Hold on, it wants me to go to the next slide, so we'll wait on that. But we're going to do the chart, and then we're going to just confirm with our breaker or our fuse. So that's why I put this slide up. It's a reminder, it's 2 steps. Step 1, check this chart. Step 2, make sure that's going to work with your fuse or breaker. So let's step through a couple of those. Yeah, I made it bigger. All right, so intermittent load. Let's say we have a 28 volt system. And I need to kind of what we care about, right? I need to supply however much power to my component. So it's going to draw 13 amps. So this is pretty much the info we need because we already said it's intermittent. So we're going to go to our chart and figure out what size. So we start off with 28 volt. So we're going to start in the top left. We're going to go say, okay, 40 foot. So we're going to scroll down here until I get to 40 foot. Now if I was to go all the way to the bottom, it would tell me what my allowable voltage drop is, just a FYI. So theoretically, I might only end up with 26, 27 volts at the component, but we'll go back up to where we should be. So start with 28, check, down to 40 foot, check. Now I'm going to scroll across basically until I hit my 13 amps. And if I wanted to do a fudge factor of an amp, I could, but we'll stick with 13. So I'm going to scroll across. Now, my brain has a hard time with these because I start scrolling and then I'm like looking back and forth and I can't figure out which line I'm on. So instead of doing that, usually what I'll do is I'll come up here. Here's my amps. 13 amp would be right about there. So I'm just going to kind of essentially draw a line down through. I gotta be a little bit over. You get the idea, right? Is otherwise, if I'm coming across and you're doing this, sure as shooting, you're going to be on the wrong side of the line. So it's a ballpark just to get you across. So 40 amp, which is this line, I'm drawing my line across until I get to, is that the right section now? Right, so once I get there, I just drop, I drew an arrow. I drop straight down, and that tells me I need a 14.4 gauge wire. We're not going to split hairs though, and my choices are going to end up being a 14 gauge or a 16 gauge. Well, we're all about safety in aviation, so we're going to go with the larger wire, which is the smaller number. So I'm going to run a 14 gauge wire in this instance. And I'm going to be good to go. So pretty simple. Everybody that comes through SMAT, not everybody, gets to this chart and they go, man, that thing's complicated. But really, it's voltage, length, amps, bing, you're done. So yeah, we'll get you guys up here a little later in the day to do that. But that was step one. Remember, there's always 2 steps. That was step 1, 14 gauge, 13 amp. Step 2 is any wire we run in an aircraft is going to have a circuit breaker or a fuse to protect the wire. It's really important to understand that. The circuit breaker protects the wire, not necessarily the component. So I'm going to run a circuit breaker to protect the wire. And that circuit breaker, we're going to learn in airframe class more specifically, is going to be as close to where I'm getting the power from as possible. Usually that means our panel. Because if I put the circuit breaker way out by the component, well, it's not protecting all the wire between the panel and my component. So that's why usually our dashboard's full of circuit breakers is we're trying to protect as much wire as possible. So, because the circuit breaker protects the wire, what I would do is I would go over to my wire AN gauge chart. I would say, I've got a, what'd I say, 14 gauge? I've got a 14 gauge wire. What circuit breaker size do I need to protect that wire? And I go over and I say, okay, I need a 20 amp circuit breaker to protect my wire. So I install my 14 gauge wire. I install my 20 amp circuit. Uh-oh. I don't know how to spell circuit.
C-I-R-C-U-I-T.
The UIT always gets me. My 20 amp circuit breaker, and I'm good to go. Pretty simple, right? Easy enough. That's the semi-easy way to do it. Remember, the easy way is you go into the wiring diagram, you say what size wire, what size circuit breaker, and you put in what mama says to put in. That's the semi-easy way to go. Now, there's a slight complication to this, and we're going to show you that here. This worked out great because my circuit breaker is higher capacity than what my component was, right? If I have a 20 amp circuit breaker and I'm only using 13 amps in my component, my breaker's not going to trip. You can end up in a scenario where you get to this chart and you say, okay, I ran a 14 gauge wire, I need a 20 amp breaker, and oh my word, my component draws 30 amps though. So we're going to do one a minute. I'll do it in a different color just to separate the two. We'll make it red for wow, that didn't work. So we'll say 28 volt, 8 foot. Hopefully this doesn't work out. And 15 amps. 20 amps. Yeah. So let's see, I'm a pilot, I'm sitting in the cockpit. Maybe it's my landing light up front. It's only 8 foot away from my cockpit, so it's a really short wire, right? I think this will work. So we come back up, 28 volt, 8 foot. Whoa, we're like pretty much off the chart. Should we make it 12 foot, just so we're on the chart? 12 foot, it's 12 foot away. It's a little bit bigger aircraft than I originally assumed. So we're down to 12, 20 amps. Over here, it's that one, this one. Okay, coming over 12. Well, if that line were to continue, it would intersect me right about here. And okay, I need an 18 or a 20 gauge wire. I'll go with the bigger wire, which is a smaller number. Okay, I need an 18 gauge wire because it's really short. I'm only going a little bit of distance. So to have my allowable 2 volt drop, 18 gauge wire. If I just go install that in my aircraft, I go, oh shoot, I need a circuit breaker to protect my wire, right? Let me come over here to 18 gauge wire. What size circuit breaker do I need to protect my wire? Oh, a 10. I can't put anything bigger than a 10 to protect my wire. It's not protecting it anymore. So if I put a 10 amp breaker on this circuit, what happens when I turn my light bulb on? Pop. That won't work. Shoot. Well, what if I put a 20 amp breaker in? Well, now I'm illegal because my breaker's too big for my wire according to the chart. So you can end up in this situation where you went through all the work of picking your wire out and we can't make it work. So what the solution is you run a bigger wire. So in this situation, what you would do is you'd say, well, I know I need a 20 amp breaker, so let's just cut to the chase, come down here and say, I need a 20 amp breaker for my lamp, so I'm going to run a 14 gauge wire. And I'm going to run a 14 gauge wire because, well, it's bigger than an 18 gauge wire, and that's what we're going to do. It's only 6 foot. How much extra weight could it possibly be? All right, does that make sense?
If you have a 20 amp light bulb though, would you max that right out on 20 amp breaker?
Probably going to do a 25 amp breaker. You're right. Yeah. Yep. And that goes back to, you're going to do what the manufacturer says. So I'm trying not to put too much fudge factor in just to keep the math straight, but excellent, excellent question. Brian.
How come the fuses and circuit breakers are the same amperage?
That's a great question, Brian. I think that's the next comment on my slide. So a circuit breaker typically takes a little bit to blow. Do I have that right? The fuse is a smaller size, right? Yeah. So the way a circuit breaker works, is that a circuit breaker? Yeah, the tricky one. The way a circuit breaker works is you have an amp draw going through there. There's a kind of set resistance inside, and it warms it up. And if it warms it up too much, which higher amperage, more warming, if it warms it up too much, it says, oh, too much, and it trips. So circuit breakers tend to have a bit of a delay effect built into them, and they tend to be a little bit more accurate because they're a bit more engineered. If we switch over to the fuse, a fuse, and they make a couple different styles, but a fuse, that's a little guy. This is only a 1 amp fuse, but a fuse is often just a wire that too much amp draw, it's going to blow up. These ones, there's not going to be much time delay on. So if you have a quarter of a second with that amp draw, probably going to blow it. They do make time delay fuses that incorporate some kind of funky stuff into them. And a time delay fuse gets closer to the circuit breaker as far as how it works, but we'd start splitting hairs and the FAA is not going to give us a whole other set of charts. So the answer to that question is just the way they trip. They're going to say, you know what, we'll let you run a little bit more power through a circuit breaker because it's going to have, I'm going to use the word, it's going to have kind of a time delay cooling effect, the same as your wire does. So if you have kind of a high inrush, but then it drops back down again, like when I start a motor, okay, we're okay again. The circuit breaker is going to be able to handle that and not just trip immediately. It's going to be like, yeah, that was a high inrush, but it went back down. Where fuses, they don't typically have that capacity. They'll trip a little faster. So then what happens is people will put a larger fuse in to handle it. Well, now we're going down this road of we're not as safe. So that's the explanation that the FAA ends up basically giving and why they do it is circuit breakers are, I'm going to say, more controlled. So because they're more controlled, they give us a little bit more leeway, a little bit more room with them. Good question. All right. Which one? I'm working on a Concorde. It's 150 foot Austin. You're my lucky victim. It's 150 foot. From my circuit breaker back to my supersonic flapper doodad. That's what we're going to be wired in, our supersonic flapper doodad. 150 foot. We're going to say our Concorde's running on 200 volts, and my supersonic flappy doodad takes, let's see, 200 volts, 10 amps. It's a really big motor. 10 amps to operate, but we only do it occasionally. Intermittent. What size wire do I need to run to my supersonic flappity doodad? He's not even going to draw it. He's just like from the back of the room with laser vision. He's gonna guess 20 gauge. Okay, I'll check you. Is this like a guess or you actually did it?
No, I actually did.
Okay, well here we go then. 200 volt, 150 foot. So we're somewhere in between, aren't we? And we'll get that a lot. 126, 168. I'm gonna go with right about here. 150 foot. Double checking ourselves. Intermittent. Yep. All right. 10 amps, so 10 amps, it's nice when it falls right on the line because then you can circle it and your students don't laugh at you. Wow, he's good. 20 gauge, did you do the next step though? Oh no, all right, let's go back to the next step. We know we have to run at least 10 amps through it. If we run a 20 gauge wire, what circuit breaker will work for my 20 gauge wire? Oh, snap. I can only run 7.5 amps through my 20 gauge wire. So, well, let me rephrase that. I can only have a 7.5 amp breaker on that wire. So, if you ran my 20 gauge wire and then you were like, oh shoot, my breaker size, oh, 7.5, it's not going to be big enough. So we would have to do that bump up and say, oh man, okay, let's bump up our wire size to 18 gauge, because now I can put a 10 amp circuit breaker in, because now I can handle the load. So, great job on the chart. Don't forget the second step if you're actually running a wire in an aircraft. See how that'll catch you? And it'll often catch you. The dead giveaway is if you get to the bottom of the chart where the lines stop, you're, as Captain Jack Sparrow says, you're off the chart, matey.
So a 10 amp circuit breaker means you can function at a like a constant 10 amp, or is that gonna break at 10 amps?
Are you trying to confuse me? I know, so the way to read the chart is I know what size wire I have, what breaker do I need to protect it? So if I know I have an 18 gauge wire, what circuit breaker do I need to protect it? So it's gonna be that size or smaller because we're protecting it. So an 18 gauge, I can put a 10 amp circuit breaker in to protect it. So if you wanna reverse that, which you're trying to do, which is what we really wanna do, you would say, if I have a 20 amp circuit breaker, let's say, so my load's 20 amp, you could say, what's the maximum, minimum, what's the minimum, see I got it backwards too, what's the minimum size wire that I could use with that? So the minimum size, if you're going this way, minimum size wire would be a 14 gauge. So I'll draw that up. Maximum breaker, if you're going to the right, minimum size wire. That'd be a good one to take a picture of, because
So that's to decide your wire size.
yeah, well, ultimately this chart is supposed to be here to decide our breaker size, but because we always got to go double check and make sure, well, in this Concorde situation, if I would have said, oh yeah, hindsight, I need a circuit breaker, I just ran an 18 gauge wire, what size circuit breaker, well he said 20, but what size circuit breaker do I need? And you go down, well, if I had a 10 amp motor and I stuck in a 7.5 amp circuit breaker, it's gonna pop.
So you would still put a 10 amp circuit breaker in there?
But I bump the wire size up from 20, I bump it up to 18. 18's a larger wire.
And that,
So because what we want to do is we want to run the absolute smallest size wire, which is the highest gauge number, right? That's the other inverse that always trips us up when we're new at this. Because if I'm running this size wire back on my Concorde is going to get real heavy. It's not going to get off the ground. So we're always trying to get the absolute smallest wire we can and be safe. So for clarity, let's run that one more time, and I think it'll clear it up for you. It is a confusing thing. So we came down to 150, we went over, we said, I can run a 20 gauge wire. So wire size, okay, I'm okay with 20 gauge, but that's only step one. So now we come over here and say, what size breaker do I need to protect the wire? Because the breaker protects the wire, and that's why I'm like, breaker protects the wire, breaker. The breaker doesn't protect the component, it protects the wire. So, what size breaker do I need to protect my wire now that I know I have a wire size picked out? And I would say, oh, I can't put anything bigger than a 7.5. Let's say I put an 80 amp breaker in. Is that going to protect my wire? No. Now, I could put a 5 amp breaker in. That'd protect my wire. But 5 amps ain't gonna cut it. So, because 7.5 was the one, that's the maximum size breaker, if I actually installed the wire that the chart said, I'm not gonna be able to run my component because my circuit breaker is gonna trip, right?
so if the breaker's rated at 10 amps, it only breaks if something goes above 10 amps? Or
Correct.
it breaks at 10 amps?
At or above, yep. Well, it'd be above, say above.
That's, because I was, yeah. Okay,
Yeah, because we're at the exact number you're saying, is that where you're going
Yeah,
with that?
that's, I was confused.
Yeah.
10 amps through a 10 amp circuit breaker, is it just gonna break when you're
Yeah,
running?
maybe I should have said 9 then?
Yeah, yeah, I got it.
Okay, that's the part.
So in a sense, the chart doesn't really help you when you're doing the short lengths. It only helps you out once you start doing long lengths and then you get more voltage.
Exactly. And that was where we were going, was on, basically, once those lines start disappearing, basically, we're just gonna skip right over to here. So if you get down below where those lines are on your chart, you're like, well, we'll just go over straight to what size breaker, because that will end up being the determining factor. All right. This is just more exercises. I am not sure if this chart's gonna show up on your tests anymore. I believe the students said last year it showed up on one of them. It was like maybe general. It's in 98 and 2008 is when they changed AC 4313 last. And this used to be the chart that you guys work off, which is funny because when you look at this, it looks like it's like 40 years old, right? It's not that old. So this used to be the chart, and what they did is they said, okay, one more step. We're gonna say, is your wire running in a bundle? Because remember how we talked about if it's in a bundle, it can't get rid of the heat, and blah, blah, blah. So they did one more step. So let's take this one. We'll go 200 volts. I shifted my numbers around, just trying to confuse me. 200 volts, 150 foot. 10.
Christina has gone over all these with us before.
All right. 10 amp. I come down. I think I'm in the neighborhood. Somewhere between 14 and, oh, we switched over to continuous use, which is why the number's slightly different, but the point will come across. So we'd come down and we'd say somewhere between 14 and 16 gauge on this one. And then we'd one more time say, hey, let me double check my 10 coming across and make sure it doesn't hit the curve. Curve 1 is continuous rating in conduit and bundles. 2 is continuous in single air, and 3 is intermittent. So basically what they did is they got rid of this chart that had essentially, where'd it go? These two charts that are separate in your book, right? Figure 11.3 and 11.2. So instead of doing just one chart, and then what you would end up doing is you would pick which curve, make sure you don't get below it. They said, this is confusing people too much. We're gonna go to 2 separate charts. But there were some questions on the written that popped up. So what happens is it's similar. If we get down below on shorter wires, typically is where we get in trouble. So I'm just gonna backtrack and we'll come up with one a minute. Okay. So if we've got a 14 volt system and we want to run it 8 foot at, that's a lot of amps, 30 amps. So 14 volt, come down to 8 foot, come over to, oh, see now I didn't do my 30 amps to make sure I don't lose my line. 30 amps. If I drop straight down, I'm basically at a 12 gauge wire that it would say to use. But what we didn't spell out ahead of time is we would have said, hey, is this continuous use or is it intermittent? And if I said, well, it's actually continuous and it's in a bundle. Well, right here, I'm down below this continuous bundle loop. So it wouldn't work. So they had you do it in 2 steps. They'd say 12 gauge. Okay, well go back up to your 30 and make sure it doesn't drop below. Whoops, we dropped below. We crossed that line. So what they would do is they just have you stop at the line and go straight down. So instead of 12, you'd end up picking a 10. So that's how that chart works. Is it was a 2-step. One was get the one you think you want to use. but then backtrack to your amperage, and wherever you hit the curve of what you were, you could drop down the line. So if it was intermittent use, not in a bundle, that one was all the way out here, and you'd go, okay, we're still good, I'd use the 12. So if you want to play around with that one, you can. I don't think it shows up anymore in reality. It's just takes the FAA a little time to take questions out of their testing software. But, so if you ever see that chart that's got 3 curves, it's just add in the last step of grab your amperage, make sure you don't cross the line of continuous bundle, continuous non-bundle, or intermittent. Does that make sense? Other than that, it's the same chart. Okay. And you would still have to do the last step of double checking your circuit breaker or fuse. All right, so reminder, easy, first choice, just do what the manufacturer says and avoid all this. But you've got to pass your written. So to pass the written, you're going to use the easy chart. And I'm not even going to teach you all the crazy steps. But if you have AC43 in front of you, if you go to, it's page 1125. I'm going to get it up on here. Page 1125. Paragraph 1167. It will start out back here in general stuff, but it'll say methods for determining the carrying capacity of wires. And basically it's 4 pages of stuff. It gives you some info. It talks about altitude. It talks about copper versus aluminum. And it starts out at basically over here where it says 2 requirements. It's going to be the wire length, the amperage, the allowable voltage drop. So it asks you all these questions, and then you check step 1. You go through a chart on step 1, and then step 2, and then step 3. And then after you do that, you've got to get, that's just the chart we did. Step 3, easy, 3 steps, right? Example 2, there we are, that's where I wanted to be. 1169, the hard way, you end up with step 1, step 2, step 3, step 4, step 5, step 6, and inside those there's even more math. And these ones start asking questions like, what's your altitude? What is your wire rated at for amps? Continuous duty, not continuous duty. And the bundles. So they're going to look at what altitude you're flying at. They're going to look at what your rating is for the wire temperature. They're going to look at a bunch of other stuff, and they're going to give you a fudge factor. They're basically going to say, you know what? From what we told you you could do on this chart, you're not quite that high at altitude, so we'll give you an extra 20%. You know what? You're using a wire that's rated at more heat. We'll give you an extra 20%. So they'll give you a bunch of little bit extra leeway. And one of those is even on the breaker. And if you read the breaker one, I don't know if anybody read it, but if you actually read the breaker one, it'll say wire bundles of 15 or more with wires carrying no more than 20% of the total carrying capacity of the bundle is given here. And near that, it'll say, hey, if your wire's not in a bundle, we'll give you an extra, I think it's 20% is what it talks about. We're going to go into that in a lot more detail when we get into airframe and power plant. But there are ways that if our charts that we learned today came up with a 12 gauge, that the FAA will be like, if you do all the math like an engineer, we'll let you run a 14 gauge. We'll let you do it. But as an A&P, we're so far down the line, you're not gonna do that. You're gonna check what the manufacturer did, you're gonna do the easy way, and you're not gonna be an engineer, unless you really want to. But you could if push came to shove. Smallest wire you can use with that breaker. And that is pretty much where we're going. Insulation for our video, and then we're done. Has a temperature rating. It's got a resistance, so if you actually put an ohm meter across the insulation, you'll get a certain ohms. So that's a rating on your insulation. And then it's got a dielectric strength. That word dielectric, we remember, has something to do with, let's say, static and how it gets polarized and stuff stacks up. This one, basically what they're saying is how many volts we can put to this until we get breakthrough voltage. Once we have breakthrough voltage, it basically, the simple version is it'll burn a path through, and once we burn a path through the insulation, then we get a runaway effect of it gets really bad. So resistance is, well, it's weird how they do it. It's kind of like you might get a tiny little bit of leakage, kinda, maybe. Where this one, it'll be a voltage where it says if you exceed this voltage, we're gonna damage the insulation. So this one's more of a, how good it does. That one is it's damaged and beyond repair. So we might have a 450 volt rated wire that comes off dielectric strength, where they might just give a resistance value of the insulation, but it's not a, if you exceed a voltage, it's shot. All right, video, and then we're out to lab. Where's my mouse?
The following tests, performed for the NTSB, show two issues relating to the short circuit and arcing properties of aged aircraft wire insulation. The wire is insulated with Boeing material specification BMS 1342A, known commercially by the Raychem trade name Poly-X. The wire was removed from a Boeing Model 747 airplane after more than 25 years of service. For comparison, tests were also performed on wires insulated with a tape-wrapped aromatic polyimide, sometimes referred to by the DuPont trade name Kapton. The polyimide wire is MIL-W81381. The first property demonstrated is the wet arc tracking resistance of the wire. On aircraft, liquids do get onto wires, whether from spilled beverages, leaking laboratory water, condensation, or moisture absorbed into salt or other surface contaminants. This liquid can lead to wet arc tracking, which is a process where a conducting carbon path is slowly built up over time due to low-level electrical discharges on the surface of the wire. This photo shows an example of carbon buildup on 81381 type wire. The electrolyte used for these tests was a 1% saline water solution. Wet arc track tests were repeated with laboratory waste known as blue water. The Safety Board investigation documented numerous cases of metal shavings on wire bundles and between strands, and was interested in examining the effects of metal drill shavings on the wire insulation in abrasion tests. One test measured the damage caused to the insulation by the metal shavings during abrasion of the insulation. A second test recorded the properties of short circuits between wires that the shavings created. The wet arc tracking resistance test followed the Society of Automotive Engineers standard AS 4373 4.5.9 method 509. In this test, a wire bundle composed of 7 individual wires is placed in the test apparatus. The top 2 wires of this bundle each have had nicks put in the insulation so that the conductor is clearly visible. This represents damage that frequently occurs in installed wires due to environmental aging or physical trauma. These wires are connected to a 10 kVA 3-phase 400 Hz generator with 120 volts line to ground. There are 1 ohm resistors in series with each wire along with a 7.5 amp aircraft circuit breaker. During the test, the electrolyte is dripped onto the bundle between the damaged spots and the 2 top wires, and the results are recorded with a digital oscilloscope. The first example was performed using a 1% saline solution that was dripped onto the area with a nicked wire insulation. The wire insulation type is Boeing Material Spec BMS 13-42A, and the wires are 20 gauge. Soon after the test begins, pinpoints of light can be seen near the edges of the nicks. These are visible scintillations, or tiny arcs, that can slowly degrade the surface of the insulation. As time goes on, the scintillations become more intense and the surface of the insulation chars. The resulting buildup of carbon acts as a conductor on the surface of the wire. Soon, a larger flash of light with an accompanying popping sound occurs. As time progresses, the pops and flashing become more frequent. Examination of the oscilloscope recording of voltage and current from a flash event reveals a classic arcing waveform. The blue line represents the voltage between the two damaged wires as time progresses. The first cycle on the left shows a normal 400 Hz sine wave. However, the next cycle shows that the waveform has become distorted and that the voltage has collapsed into the waveform of a classic arcing event. The voltage then returns to its normal waveform as the arcing does not continue. The red line representing the current in the wire shows that to the left there is little to no current. However, during the arcing event, the current rises to a peak of 65 amperes. From the voltage and current waveform, it is easy to determine the electrical energy in the flash. We see here the power spike during the flash is 8 kilowatts. The total energy in this flash was 4 joules, which is the energy needed to melt 6 milligrams of aluminum, equivalent to a fraction of a paperclip. Damage to the surrounding wires took time, but was documented during these tests. In addition to transferring energy between wires, arcing has previously been found to generate radio frequency noise and ignite flammable materials. Again, as time progressed, the flashing becomes more frequent and intense. The insulation of other wires in the bundle are damaged until they also become involved in the flashing events. Please note that at no time during this test did a circuit breaker trip. A second bundle of the sample type wire was tested and had similar results. One of the primary factors in the intensity of the electrical activity during this type of test is the chemical makeup of the wire insulation.
All right, I'm going to go forward. Part of this is, we'll talk about it later. It's boring to trying to bring it up. That's the
We see that there is a strong burst of arcing after several minutes of scintillation. The sample becomes dormant until another burst of strong arcing occurs. This burst of arcing is stopped with the tripping of a circuit breaker. The results of this test were more akin to the arcing in the polyimide example than the first
All right, so that was a little bit different. Wire.
frequent.
So, kind of boring, and he's all technical and blah, 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 but a couple things to get across. One is, like, we assume, oh, I got a breaker in there, it'll protect the wire if something goes wrong. That went on for 20 minutes, sparking, arcing. Let's hope we don't have any gasoline in the neighborhood. What we'll talk about in airframe class is that's why we never run flammable what did they simulate the cuts in the insulation to begin with, right? What did they say caused them? Yeah, metal shaving. So when you guys are doing your riveting and riveting class, you're like, oh, I'm gonna go in, I'm gonna drill something in the aircraft, drill it out, and mount your thing, and well, where did all the shavings go? Well, hopefully not down onto the wires down below. Especially when you picture wires in bundles. I got a bundle of wire all tied together in zip ties or lacing when we get to there. And your little shaving drops down in there, and now it starts working in, and now it's stuck between two wires that are moving, and it's gonna cut through that insulation eventually. So we wanna be really, really careful, if we're doing any sort of drilling in an aircraft, that it's not as simple as just when you're done, chop back it up, because it might get in between the wires, is, hey, if there's wiring anywhere near where you're at, like, cover that up. Like, get it all covered so there's no way you could drop any shavings down in your wire bundles, in between your wires, stuff like that. But usually we just see airplanes on fire, so that was a good video to be like, oh, it might not necessarily go. It can take 5, 10, 20 minutes as they slowly burn and arc and get there. So for you pilots, I like to teach kind of from a pilot perspective. If you go, I think I smelled something. No, I'm fine, but you might have smelled something. So be excited and be thinking about what are you going to do? Where's the closest airport? What's going on? All right. I think that was it. The end. All right, lab time. Any questions? I didn't grade any of your stuff yesterday. I'm going to hopefully do that this afternoon. Wednesday, tomorrow, we have troubleshooting, which is basically going to be going over some complicated wiring diagrams to give you a vague idea of what they're talking about, because you guys don't really know the components in them yet. And then it'll be a review for the exam Thursday.